All right, one more time, we'll try this again. So we were talking about the K for this process. And I wrote that the K equals the AG NH3 2 plus over the AG plus times the NH3, and I forgot to square it, but that's the expression that should be there. And that's equal to 1.5 times 10 to the 7th. Again, that came from table 16.4 in your textbook. My overall process is AgCl plus 2NH3 going to Cl minus plus Ag, and that shouldn't be there. It's the AgNH3 2 plus, okay? So that's what that looks like. That's my overall process. Now, since I have a K for both of those things, so I have a KSP for the AgCl going to Ag plus and Cl minus, and then I have a K for the Ag plus the NH3 going to Ag NH3 2 plus. In order to get the K for this overall, the K for this is going to equal the KSP times the K complex, which technically this is, which is the 1.6 times 10 minus 10. Sorry, I was thinking about our last problem. Times 10 minus 10 times the 1.50 times 10 to the 7th, which of course we can do some happy math with. Turn the calculator back on, and we have 1.6 second EE negative 10 times 1.50 second EE7, and that gives me 0.0024. Okay, so looking at my slides one more time, let me see if I can talk about that. And 2.4 times 10 to the minus 3 is what we get from that. Now, when we have that particular value, that's going to govern how much of this product we get from this reaction. So if I set up my ICE table for this overall process, then I'm going to have AgCl plus 2NH3 going to make AgNH3 2. Nothing is working tonight. Awesome. NH3 2 plus Cl minus. Okay. Knowing that this is solid, that's not going to appear. I know that I can have my 2NH3, which is the 1.0 molar. I have my no initial AgNH3 plus, and I have no initial Cl minus. Okay. Having said that, my change, I'm going to have a negative X for the NH3. I'm going to have a plus X for the NH3 2 plus, and a plus X for my Cl minus. We then end up with that expression, the K being K equals Ag NH3 2 plus times the Cl minus over the NH3. And we make the assumption, oh, and the NH3 is squared, I apologize. And we make the assumption that the X is small. That's going to be equal to the 2.4 times 10 to the minus 3. We make the assumption that the X is small here. That means that we're going to have our 2.4 times 10 to the minus 3 times the 1.0 molar equal to the X squared, because I have an X for this and an X for this. Therefore, we're going to take the square root of that. And hopefully that gives you the value that I'm looking at. So second square root second. Oops, I forgot to do something. Oh no, that's right. And that's 0.048, yada yada. Now let's see if that's what I wrote over here. And it is. So I have rounded this to one decimal place on here, which it should be 0.048 as opposed to that from my calculator. And then I've taken that away from the initial concentration to get my equilibrium concentration of NH3, Ag, and the both the cation and the anion. That gives me a much larger solubility for Cl minus than when the NH3 wasn't present. Okay, so it's a much bigger value. Awesome, awesome. We love it when it's a much bigger value. So that's our complex ion equilibrium. So as opposed to reducing things because of the common ion, we've now put ourselves in a situation where we can increase that solubility by adding something else to it. Questions, comments, problems there? Hopefully not, but you know what the deal is if there are. The last thing we're going to talk about is gravimetric analysis, and hopefully we can get through this without having to make another part of the video. So we can selectively precipitate groups of cations out of a solution by adding particular anions to that solution. All right, and what you see in this table here, and where's my view? So what you see in this nice little diagram is they say that there's a containing ions of all cation groups. We add HCl and we get AgCl, Hg2Cl2, and PbCl2. In my first precipitation, we filter those off. Then we have the rest of our stuff. We have H2S, and then we can get our group 2 precipitates. So CuS, CdS, HGS, SNS, and Bi2S3. We then take the rest of that and add NaOH, and that's going to precipitate out a whole bunch of other things. And then we can add Na2CO3, and that's going to give us the foam. Okay, so that's one of the ways that we can look at this. One of the ways that you may see this, there is a table of KSP values, and you may be asked to look at that and say, okay, I have these two cations. I want to be able to separate them. What can I add to them to get them to separate? Now, if you have two cations who react with the same anion, and that the power, the 10 to the whatever, is more than 3 orders of magnitude, then you can use that as a way to separate the two, because one will precipitate before the other one. You can filter that, collect it, and then you'll have the other one that you can then deal with later. All right, so that's how we talk about that. Now, do you need to know all of these details? That's up to you. I mean, it's useful if you want to know how to precipitate something like that. But again, an image like this could very well be useful. So you might see on one of these tests an image like this, and I might ask you, how could we separate a group of cations? You know, what would you have to do at each stage to do this, that kind of thing. Or it could just be that you're looking at a table of K values to see what's going to precipitate and if it's going to be effective. And like I said, it needs to be variable by 3 orders of magnitude to make that work, okay? So questions, comments, problems about that? Oh my Lord, we finally got to the end. So better, more pieces than never, right? So we'll get this posted. I apologize for it being in as many pieces as it is. Like I said, we're working on this. I'm sorry this is ugly for you, but this is what it's been like to try and record this for me. So I'm sharing the wealth. I'm going to stop my share here, and I'm going to stop the recording. I hope you guys have a good night, and I will talk to you again soon.